So today we are going to. Today is finish proof of Atiyah-Singer. For Dirac first and generalized Dirac. Okay, let's see. So we had this operator before, remember? We have this operator L equal to, we came across this operator at least, minus sum over P d dxp minus 1 over 8 theta pq xk. Pk, sorry, squared. So this operator goes from, you remember, C infinity, or in fact germ of functions near 0, but I just write it like that, Rn and Clifford algebra of R. Okay. Well, the only connection to our manifold in geometry is this theta pk. So theta pk is R pk. I mean, this is a sum. So R pk, alpha beta, E alpha, E beta. And the summation is over alpha and beta. So this acts by exterior multiplication. Okay, now where this R, pk, sorry. I mean, R, pk, alpha beta, dx, alpha veg, dx beta. This is a curvature 2-4, right? Again, summation is understood, but let me put it anyhow. So this is this, this belongs to omega 2 of some open set U we are working on. Not really, yeah, for any P and Q belongs to omega, P and K belongs to this. It's this curvature 2-4. Okay, so, I will come back to this operator again, but let's just take it as is. And our goal is to construct heat kernel for this. We want to construct actually less than heat kernel. We want to construct only fundamental solution for this. So the goal is, first goal is construct fundamental solution. Okay, now we are going to, so of course, this is antisymmetric because of symmetries of Riemann tensor. This is antisymmetric in the first two variables. Okay, so this is RPK is equal to minus RKP. So the idea, so these are like differential forms, right? And so this is a differential form. You multiply these things by Clifford multiplication, then you get Clifford algebra elements again, if you go back and forth. But we are going to assume that these are numbers. Can assume, so let me write it like this, can assume theta PQ, theta PK is an antisymmetric matrix. In that case, then this becomes really just a vector valued differential operator. If these guys are just numbers of any kind, then this is just an honest differential operator acting on this algebra of vector valued functions on Rn with some huge dimension in the range. But still, it's a usual differential operator acting on vector valued functions on Rn in that case. If we assume these guys are just numbers, so it's a skew-symmetric 2n, 2n by 2n matrix. Well, this is n is the dimension of the manifold, right? Now, why we are allowed to do this? The reason is that the fundamental solution that we obtain is going to be analytic in these terms. And then we argue that we can replace the entries of that analytic function by this matrix. Because this matrix of forms is nilpotent, so this analytic function is going to be convergent and everything is, it's going to stop at finite number of terms, after finite number of terms. And everything is going to work out. So we'll get an expression. So that's the kind of idea that allows us to switch just to, for the moment, to this skew-symmetric case. Okay. So this being so, now we are going to use a basic theorem of linear algebra. That's the structure theorem for skew-symmetric matrices. So this is, we call linear algebra again. And any 2n by 2n skew-symmetric say matrix. Actually, this result has nothing to do with real numbers or complex numbers. It's true over any field. So it's a purely algebraic result over F. Maybe just to be careful, you assume characteristic of F is different from 2, but even over finite fields in general is true. Can be, I would say is similar to a matrix of this form. So this matrix is going to be block two by two matrices, so on, like m of them, 2 by 2 matrices, but each block is going to be of this form, 0, theta, minus theta. This is kind of basic skew-symmetric 2 by 2 matrix. It's going to be necessary of this form because elements on the diagonal have to be 0 and is a skew-symmetric, so this is necessary of this form. So after you choose the suitable coordinates, going in that coordinate, your matrix kind of untangles. It becomes like this. So this is such forms, by the way, maybe you have heard it in a different form. They are called symplectic forms. Symplectic or alternating two forms. This is symplectic forms. So you see, when you have such matrices, you say you have a symplectic structure and your vector space. And this is basic structure theorem for symplectic structures. They can always be brought into this standard form. So there is no invariant for this symplectic form in this sense. They are always this form. Okay, so that's so if you choose then such a basis, this differential operator decouples into direct sums of operators on 2 by 2 space of 2 by 2. Okay, so let me write it like this then. Remember, this n is 2n, which is dimension of n, or manifold, right? So then if you go into this, I mean, of course, we just went into a local thing, basis. So if you go in that, basis for Rn, as I said, differential operator decouples and gives you a very simple differential operator, which is of this form. So then, let me write it now. So then this L becomes in that basis, such a basis, L is equal to direct sums of operators of the form. Again, I just use the word L, but this L is really just a 2 by 2 case. So a special case of n equal to 1 now. So in that case, L is going to be of the form minus ddx minus theta y over 8 squared minus ddy minus theta x over 1 over 8 squared. So this goes from, C infinity of R2 and R2 and R2, R2 and R or C to itself. So this is a differential operator in that form. And so you can, by the way, write it now as L0 plus L1. But L0, okay, so then you have to square these things and write it in terms of Laplace operator and then some other operators. It will emerge because squaring this gives you a d2 dx2, squaring this gives you d2 dy2, and you add them and you untangle again. This is L0 is equal to minus d2 dx2 plus d2 dy2 minus 1 over 64 theta squared x2 plus y2. It's one piece. The other piece is L1 equal to 1 over 4 theta x dy minus y ddx. Okay, so this is now a kind of important observation. So we write L as sums of these two things. And of course, remember this L0 now is itself sums, direct sums of two harmonic oscillators, right? Because on the x direction, this is harmonic oscillator. In the y direction also, this is another harmonic oscillator. And it's decoupled again, L0. And L1 is this strange operator, but after all, it's not so strange as we'll see. This operator has a very interesting meaning. I'll mention and we'll use it in a second. So it's just. Now here is the idea now. Fundamental solution of, so let me write it like this. Since, you just say since L0 is rotation invariant, I mean this operator is rotation invariant. So the fundamental solution of L0 must be rotation invariant also. Its fundamental solution is also rotation invariant. So fundamental solution, so its fundamental solution, I just say fundamental solution, is also rotation invariant. Now, you may wonder why this is true. If you think about it, this is a more or less obvious statement, but I ask you to prove it. So why? Maybe a little exercise here. It's good. If you have a rotation invariant operator, it's PDE, for example, in plane or in Rn, its fundamental solution is also rotationally invariant. Okay, so now if you look at this, this operator actually, so what is this operator now? It's L1. L1 actually kills all rotationally invariant operators. This operator L1. I'm going to argue. Now L1 annihilates all rotationally invariant functions, like I said. You see, I mean, the reason is that this, what is this vector field, x dy minus y dx? The other way to write this in terms of usual notation, calculus notation for vector fields, is that this is minus y and x, right? This is this vector field that we learn in calculus to write. Now, this vector field is orthogonal to radial vector. If you look at this, minus y x is orthogonal to xy. So this vector field is actually generates the vector fields that's tangent to circles at that point. So, okay, so this vector field is this one, so minus y and x. So here is, for example, x is at this point, for example, if it is 1 and 0, so I'm going. So which one is it, by the way? Minus y and x. For example, here, yes, it goes like this. And so on. It's this vector field that's orthogonal to the radial vector field, which should be this one. And this shows that now what is a rotationally invariant function? A rotationally invariant function is a function that's constant on each circle. That's what it is, right? So if you compute this fundamental solution of L0 on each circle, because it is rotationally invariant, it means that it is really constant on this. Now, when you compute, you apply this vector field, this differential operator, because it is constant, it is differentiating along that vector field. So it's 0. That's the idea. So because of this algebraic form of L0 and L1, but because now L1 annihilates all rotational invariant functions, it follows that the fundamental solution of L is just fundamental solution of L0. So that's it. So the corollary is that, corollary of this fact is that fundamental solution of L is equal to fundamental solution of this one, which is L0. Okay? So we are down to computing fundamental solution of L0, but fundamental solution of L0 we have already computed. It's Mailer's formula from last lecture. So let me write it down. Just this sort of explanations. So, but L0 is basically two copies of harmonic oscillators. L0 is equal to two copies of harmonic oscillators. So then here is a fact that if you have direct sums of these two things, the fundamental solution is going to be the products. So Mailer's formula gives the fundamental solution of L0 as follows. So, but there is a complication. It's not a complication, but there's a negative sign here. In harmonic oscillator, so this is not really harmonic oscillators. You see, the operator is this one. You see, minus d2 dx2. I should write usual derivative because this is I'm on R now. Minus 1 over 64 theta squared x2. This is the operator that we have. But harmonic oscillator was minus d2 dx2 plus 1 over 64 theta squared x2, right? That's what we had. We had positive. Here is negative. But that's not an issue. In the formulas, we just replace theta by I theta. Just change theta by I theta, everything works. Because fundamental solution has nothing to do with, I mean, it's analytic function, and it can be applied in most cases. Just from here to there, you switch theta to I theta. That's all. Okay, so, I mean, as follows, I should say. Okay, so let's recall now Mailer's formula. So we get the expression which is, so WT at 0, this is equal to Mailer at 0, 0 for I theta. Okay, so the expression that you get is square root of I theta over 8 over 2 pi sine hyperbolic of I theta e over 4, which is really just 4 pi t. You can also write it as 4 pi t minus half times IT theta over 4 over sine hyperbolic I t theta over 4. Yeah, so that's a square root. Okay? So this is the formula. If you look at your notes from last lecture, Mailer's formula, it was this times exponential of -1/2 x squared and so on. But we are evaluating at 0. We are interested only at 0. So we just at the pole of the coordinate system, center of the coordinate system. Because if you know it at that, and then you repeat for every point, and then you have got the expression. This was the idea. So this is okay. So we get this expression so far. Okay, now I can write the statement that we want to prove after all. So this is, any questions by the way? Okay, so now let's just start the proof then. So this is the theorem. So this is Atiyah-Singer for Dirac. And this is a proof after Getzler. This is Getzler's proof. And this is, I think Rowe's book is really a great exposition. But there are a lot of details that you have to fill in. I mean, there are, some details. So, but the ideas are greatly explained in Rowe's book. Okay, so the theorem is this. Now let M be a spin even dimensional manifold with Dirac operator. Let D be equal to Dirac operator of M. Then index of D plus. Remember, this D is self-adjoint, as we saw, so its index is 0, so we divide it into 2 parts, and we take half of it, and that's the index, that's the relevant index question. Index of D plus is equal to integral over M, a hat of Tn. Usually, you write this as pairing between the a hat genus of tangent bundle and fundamental class. That just means integration. Okay. Just means this is okay. Right now it's just a formality. This is fundamental class. You're integrating this over the manifold, and this is the expression. It's a differential form that has many components, and we just look at component of degree n. It gives you that component, and you integrate that form over m. You get an integer, and that integer index of t. So that's the result we were looking for. We were trying to prove. I mean, the whole thing is, of course, is one of the main results of the course is this one. So. Okay, so you see that now the idea is that this a hat, the expression of a hat was x over basically sine hyperbolic of x, where you replace x by curvature tensor. That was the expression of this characteristic class. And we need here this hyperbolic x t over sine hyperbolic of t, basically a square root. And But still there is a, there is some distance between the two statements, so it has to be justified. So let me just now prove. Because we took the following steps so far. Two following steps. First of all, we introduced this operator d lambda, which is equal to 1 over lambda m lambda inverse d m lambda. This d was a local expression for the Dirac, and this is a scaling of operation. That the scaling was done by in a careful way, looking at Clifford algebra. So this is from last two lectures. And now saw that actually I did not prove the second part, but that's not difficult. This is a calculation in local coordinates. Okay. So d lambda squared actually converges to L as lambda goes to infinity. Now, if this L is this operator we computed its heat kernel here, so it's a much more simplified operator. That's we computed heat kernel in terms of heat kernel of the harmonic oscillator, more or less. So this converges to that. So the fundamental solution Wt lambda for d lambda squared converges to fundamental solution for L. It's d lambda squared is just like that, converges to L. So fundamental solutions also converge to fundamental solution. This is also, at least at the formal level, is not difficult to see. So that's a thing. And then we had a formula for this Wt lambda. Because this Wt lambda, this d lambda, the fundamental solution of d lambda squared, we can just read it from fundamental solution of d. So this was the next step. Also saw that this Wt lambda actually is equal to lambda to the power minus n m lambda inverse W t over lambda squared. Where Wt is just fundamental solution of d squared. So now the idea, okay, so far nothing has happened in a way, because okay, so there is this operator and fundamental solutions converge to that, and but at the end, remember, we want to compute the index, and we want to compute one particular term, because we know that there are millions of terms, and we don't have access to those terms. But there is one particular term. So, but the magic of this trick, this deformation argument appears now. Okay, so the magic of this Kessler deformation appears now. Okay, there are several magical things, but really, the main thing is this last step of the deformation. I mean, this d lambda squared going to L is in the observation. So what is this observation I'm talking about? So first of all, let's write the fundamental solution Wt of T squared. So let me write it. Okay, so did I say Wt is fundamental solution of T squared? Right, yes, that's good. So let Wt at x, so this is given by 4 by t, in general we know that, times, oh, there is this term, e to the minus, yes, absolute value of x squared over 40 times sum. So let me erase this part because it's part of the explanation. This is equal to sum over L and E, T to the L, and L E of X, E T. So, I mean, L goes really from 0, I mean, if you want to be more precise, goes from 0 up to infinity. And E is just the indexing of basis of Clifford algebra, right? Because each term here, so this is a double sum. Each term for each L, this is a finite sum of element inside the Clifford algebra because the sections is a Clifford algebra valued thing. So this belongs to Clifford algebra, and this E is indexing for Clifford algebra, and E tilde is really just a Clifford algebra element, right? So this belongs to Cliff. In the basis, part of the basis for Clifford algebra, as we have been using this notation. Okay, then using expression of Wt lambda in terms of expression that I had over there and I just erased, in terms of Wt, you get the following formula for Wt lambda of x. You get that this is equal to 4 pi t. This is equal to, yes, let me write it as 4 pi t as usual, of course, minus n over 2 e to the minus absolute value of x over 2 over 4t times sum L and E. Okay, sum L and E. Yeah, TTL, NLE. TL was there. This NLE of lambda inverse of x. Yes. And then E tilde times lambda to the power minus 2. You get weights because you introduce weights, and we know the relation between this and that. So you have to introduce weights over there appropriately, and then this corresponds to n lambda inverse operation that was in part of the formula. You get lambda to the power minus 2L plus degree of E tilde, which is this one. This is degree of this term. Yes. Okay. So, and we know as lambda goes to infinity, Wt lambda converges to fundamental solution of L computed earlier. So now this relation that we have here, this is quite crucial. Remember, in computing the index, okay, so let's recall now Brazil's formula. The Brazil formula was that inside the Clifford algebra, to compute supertrace, we just had to compute the top part of the thing. So this was that for any C belonging to Cliff, right? I mean, supertrace of C was really equal to, what was it? I mean, the expression that we had was just, say, C1 to N. This is the top part. If C is equal, well, there was some coefficient here, by the way, minus 2i, I believe, to the power n. So if C is equal to sum C E times E tilde, right? E in subset of 1 to n. Okay. So this was this was Brazil formula, purely linear algebra formula for superlinear algebra. So to compute supertrace of an element in Clifford algebra, you look at the top part. That's it. But there is some adjustment, minus 2i to power n or something. Okay. So this is one thing. Now we have also this Atiyah-Singer. So plus Atiyah-Singer. What was Atiyah-Singer? Atiyah-Singer said that index of D plus, remember, is equal to integral over M supertrace of K T XX. I mean, this is really like usual supertrace because this is the integration part. This is the Clifford algebra supertrace. So what is this? This is now the term that corresponds to, I mean, so let me write it like this before. I mean, here there was one step before this. This was really supertrace of exponential of minus TD squared, right? And to compute these things, we argued that this should actually be equal to, in this picture, it really should be n, this function n over 2, 1 to n. We argued that the only part that survives after integration is the part that in the expansion that corresponds, because there is this t to the power minus n over 2, and inside all powers of t are positive, so they should cancel each other, except there is one part which is a constant, and that constant corresponds to L equal to n over 2. This n over 2 by minus n over 2, they cancel each other, they give you a constant, but then there are zillions of terms inside, but among those, then you have to pick just the top part. So you see there are two arguments going on. So both are needed. I mean, Brazil and Atiyah-Singer, and of course the deformation argument. So this is the magic of this formula. And if you look at this formula, star now implies so you kill a lot of bad things. So let me just write it here now. Okay. So star implies that the coefficient of T0 in the asymptotic expansion of L is exactly this term that we are looking at. We are looking for is this term. And I just denoted by this n over 2, 1, 2, n. Brezin says that this is the only term that matters in computing the index. And now, okay, so this is just from this formula. If you see, if L is equal to n over 2, here you have to put the top part. I mean, this is kind of clear. So here you have to take the top part, L is equal to n over 2. So, and then t to the L over 2 minus t to L over 2. So this is really a kind of the magic of this deformation argument. So this is equal to, I mean this minus 2L plus E, have to be equal to 0. L equal to n over 2. Okay, so now what we have to do, we have to compute the coefficient of T0 in the asymptotic expansion, or I mean in the heat kernel, or actually fundamental solution for L. That's all we have to do. Okay, so that's the final step of the argument. Okay, so finally, let me write it. All remains to do is to find the coefficient of T0 in the asymptotic expansion. I mean, same thing, fundamental solution, in the fundamental solution for L. Okay, but this, we already know the fundamental solution for L. We found it in terms of T. We have complete information about fundamental solution. We just have to take the constant term of that expression. So Taylor expand fundamental solution and find the coefficient of constant. So Taylor expand. So what was this WT now? This WT that we got was 4 pi t. At 0, it was 4 pi t minus n over 2. This was like it 8 over 4 divided by sine hyperbolic of it 8 over 4, 1/2. And of course, finding Taylor expansion of this function is not difficult because this is just t over sinh t square root. I mean, that's you just have to expand it and invert this function. That's easy. Okay, so Now you can just write the whole thing as so after Taylor expansion, because this function is analytic at 0. Find coefficient of t to the power n over 2, because that's the coefficient that cancels with t to the power minus n over 2. Find coefficient of t to the power n over 2. We get this equal to 4 pi t minus n over 2 plus n over 2. So this was n from beginning. Term Taylor coefficient of a hat minus 2 pi I t theta. This becomes equal to 4 pi t minus n over 2 pi I. There is this 2 pi I coming out. N over 2 cross n over 2 coefficient of a hat of 2 pi t, of t theta, sorry. The 2 pi we pulled it out anyhow. 2 pi I we pulled it out minus t theta, or t theta. So that's equal to I over 2 to the power n over 2 cross top part of a hat. And now, so index, again, I just write Gaussian index of t plus turns out to be equal to minus 2i power n over 2 integral this n over 2 1 to n, right, of 0. But this part we computed, this is I over 2, n over 2. So they cancel each other, minus 2i, n over 2. This term there is I over 2, n over 2, times I over 2, over 2. So this is equal to 1. And then there is integral of theta. Remember, this theta is the curvature matrix. I used the notation R before, but this is our R, which is curvature matrix. Well, I mean, this is curvature matrix divided by 2 pi. So this is really R over. What was the formula for a hat genus? Do you remember? There was not 2i division. There was R over, was it R over 2 pi or 4 pi? It was R over 2 pi maybe. I've forgotten the formula myself. But it's not 2i, it's 2 pi. I mean, without I, but I'm not sure. Maybe it's 4 pi, but things match. They just really match, they give you. There is one thing you have to worry about. That's we switched between I theta and theta. And this has to do with the fact that we changed minus 1 over 64 theta squared x2 to 1 over 64 theta squared x2. And this theta to I theta business is because of that. That's you can just figure it out. That's not the thing. So this is basically the idea. I mean, okay, there are some details you have to pay attention, but really, I mean, that's the idea. Okay. So let me make a comment about this proof. Okay, as we saw, there are many ideas that went into the proof. You see, we had Atiyah-Singer, we had Berzin's formula, and we had this Getzler rescaling, and all these things. So the main idea at the end, which was this Getzler's rescaling, and of course the heat equation, overall approach based on heat equation was also fundamental. But this Getzler rescaling, the idea was that you have this operator which is very complicated. You deformed it into something which is easy, essentially. At least the part that you're interested in, that part, it was very easy to detect from the Taylor expansion of this function, I think. So the idea really is the deformation argument, basically. You're deforming your operator to something you can analyze, and you know how to find the index problem. So I don't know if you have seen this sort of, so it's a very general philosophy in mathematics, the idea of deformation or perturbation. You perturb things in such a way, sometimes you perturb things because perturbed things are closer to reality. I mean, they're more complicated. But sometimes also you perturb things because they're simpler. They act in two different ways. You know, for example, harmonic oscillator, if you perturb it to quartic oscillator, it becomes something like a monster. It's very difficult to analyze, right? But in this case, was the opposite process. We perturbed very complicated thing to a simple operator, which was. I mean, by the way, I mean, this L, it's itself, I mean, the term that we want for this L, that particular term was not very bad. Was just, you know, this. So, I mean, this is kind of deformation. So. Okay, maybe if there are any questions.
Could you maybe say something about why this heat equation can come out? Like how does the guy, the Gensler, think about heat equation when there is this heterogeneous? Like, I guess there should be some relation between a heterogeneous and the heat equation, so he thought about it to prove it this way. But how does it come up?
Yeah, I mean, the heat equation idea was suggested by Atiyah-Singer and Bott, I think, at first. But they didn't know how to get it to work. So yeah, let me, maybe I think I can maybe erase this part at least. So the heat equation approach was this Atiyah-Singer idea. Remember index of, well, I just had it many times already today. Index of P plus is equal to supertrace of exponential of minus t squared. And this is equal to integral over m. This was like, well, this is just kt, I mean, supertrace of kt xx dx, right? I mean, this is like saying the trace. I mean, this is an infinite dimensional version of the fact that trace of a matrix is sums of its main diagonals, element on the main diagonal. Of course, this is super trace, but this is trace. It still doesn't matter. Now, but so this formula they knew. They knew, but it's very hard to extract information from this formula. But all you need to know is so this is Atiyah-Singer. I mean, you can push this argument a little further, say that this is equal to integral over m. super trace of just the part that you need up to some constant, because you have 4 pi t, and just the term that you need is really k. Okay, I just write u n over 2 x the volume x, right? Because this, you can expand it as 4 pi t minus n over 2 sum ui of x ti, I from 0 up to infinity. This is part of the classical theory. Everybody knew that. And this was also not very difficult to prove. This is purely algebraic idea. We proved it. So this was okay. Up to this stage was okay. But then they were stuck. They didn't know how to compute this term. As I said, this term itself is like millions of terms. If you, I was going to show one of my papers where there are like thousands of terms appearing. Then if you compute like A12, for example, U12, for example, in this case, but okay, maybe next time I will show. Anyhow, but then there was this idea of Brazil that showed that this supertrace actually can be computed in terms of the top part. Only one term is relevant, because this is an element of the Clifford algebra for the Dirac, only one. And then there was this argument of Gessler at the end that showed that you can deform your operator into something that this term can be easily computed for. So it's really like a confluence or coalescing of many ideas. Yeah, quite many ideas. But I like this deformation philosophy, because this is something that's used in mathematics in both ways, to turn easy things, change easy things to difficult things, and to change difficult things to easy things. It's a both-based trick, actually. So we can. So I want to give an exercise. Not exercise. Maybe something to think about as part of your assignment for this week. The idea is write up your favorite deformation argument in mathematics. Okay. Write up. It could be just few lines. It doesn't matter, or a page, whatever. Write up your favorite deformation argument, or proof by deformation in math. I'll give you an example. For example, fundamental theorem of algebra has been proved like this. One proof is just like this. E.g., in that case, it was a homotopy argument. But there must be other examples. This is used all the time. Fundamental theorem of algebra. It could be maybe. So, is that okay now? Maybe a little more?
Well, what do you mean deformation argument?
What's that?
What do you mean deformation argument? That is...
Yeah, this is no, I don't want to make it more precise, because it's an idea that if you try to make it more precise, you just kill its charm, right? It's better to have it in a vague, formulated in a vague terms. But I know, for example, this idea is used in algebraic geometry. For example, if you want to define intersection numbers of two curves or two varieties, you deform them a little bit, and then you put them in general position, and then intersection numbers are defined in that way. So it's really used a lot. I'll be happy if you just think about this and maybe give a 3-line, 4-line, 5-line homotopy proof of fundamental theorem of algebra. That's a good example. Maybe I'll give another example of this, how the deformation argument goes, and then I will give you another. So shall we take maybe 7 minutes break? Or? Okay, maybe I'll just give this argument now. So, and then, so here's a nice example. So here's example. Okay, so let's consider Hilbert space H equal to L2 of n. So this is the set of all sequences A0, I don't know, A0, A1, A2, such that some absolute value of AI squared less than infinity. So this is a Hilbert space. Now, any operator F continues. Okay, so you can define an operator TF. I mean, for any function, I mean, continuous, from L2 of n to L2 of n in the following form. So what is TF of some AI, for example? I mean, what is TF of this? You do something very strange. First of all, from these AIs, you construct a function. Construct a function which is like sum. So function G, which is sum AI, e to the I N O, okay, AK I put. E to the, I mean, here is AK, e to the I K 2 pi theta. I mean, this is like G of theta. K from 0 to infinity. I mean, this is a nice L2 function. It's a nice function. And then what you do, you just take Fg. It's again a function on L2 of S1. This belongs to L2 of S1. You take its Fourier coefficients, go back again. So this is the Fourier coefficients. So you get something like B0, B1, B2, and B minus 1, so on. And then finally, you extract only this part. So we just say TF of A, if this is A, is equal to B0, B1, B2, and so on. So this is called, by the way, Toeplitz operator, defined by F. This is Toeplitz operator defined by F. Now, there is a fact which is interesting. I mean, I just use it. I mean, you can see proof in many books. The fact is that if f of x is different from 0 for all x belonging to S1. So in other words, we are saying this f goes to not 0, never vanishes. So this goes somewhere, it never vanishes and comes back again. Then this operator is actually Fredholm. TF is Fredholm. So Fredholm is like this operators that we have been looking at. They have index. So i.e., so let me write it here. I.e., index of F is equal to dimension of kernel TF minus dimension of co-kernel TF. is less than infinity. You see, I mean, this is an operator that's going from Hilbert space to Hilbert space. You can show that it's a bounded operator and it's threshold. So you take it. So the question is now, what is index of TF? So this is kind of index problem. This is kind of index question, right? We are interested in knowing the index of this property. So the answer is this is equal to minus winding number of F. This is the winding number. I mean, winding number is, what does it mean? It just means you compute how many times the circle is wrapped around the origin after you apply this function f, right? So because you get a curve like this, and now you are measuring how many times this curve is moving around circle, or maybe it's not moving, then in that case it would be zero. Winding number would be zero. So this is a kind of baby index theorem. This is called, I believe it's called Noether. This is Fritz Noether. And also Goldberg and Krein. Index theorem or index formula. So this baby version was long before Atiyah-Singer. I mean, this is, but it's kind of nice to have in mind. I mean, so the question is, how do you prove it? Now, how do you prove this result? This is a nice result. How do you prove it? The proof is really by deformation. So let me give you now, first of all, I'm going to ask you to write the matrix of this. So here is an exercise. Show that TF has the matrix you see this TF goes from L2 to L2, so it's a kind of infinite by infinite matrix, right? It's a huge infinite by infinite matrix. So its matrix is going to be of this form. I mean, first of all, there is here like A0, A0. And then there is A1, I believe, A1. And A2. And then here is A minus 1, A minus 1, A minus 1, A minus 2, A minus 2. Where F of theta is equal to sum AI, I mean AK, e to the 2 pi I k theta, k belonging to Z. This is the Fourier expansion of F. I mean, any continuous function has, or even L2 function has Fourier expansion, so that's not. Of course, I mean, when I say equal, really, I don't mean equality in the sense of pointwise convergence. This is L2 convergence, so at least L2 convergence. I mean, if F is smooth, then this is, of course, pointwise even. Could be better even, but that's okay. All right, so this is your exercise, but if you look at this matrix and you want to compute its index, it's very difficult because, I mean, how do you compute the kernel of this matrix and co-kernel of this matrix? It looks very difficult. So that's where now this deformation arguments come into the game. So then proof of a star. The following idea of proof of a star is you just deform F to Zn, since f of x is different from 0 for all x. I mean, okay, so this is why we can take its winding number, right? Let k equal to winding number of f, then the form or homotope, so to speak. I don't know if there's such a word. You can invent the word if you want. The form or homotope f to this function zk. Because, you know, any continuous function, over zero continuous function on the circle is homotopic to one of these guys. This is because of homotopicity. And because index is homotopy invariant, so this is index of tzk. But this is very easy to compute the index of this operator. It's very easy. You can just show that this is equal to minus k, which is the minus winding number. So you're done. So now you have turned in a very difficult problem. I don't know if there is really any other solution for it like this. By this topological argument, by deformation argument, into something which is now very explicit. And this calculation is easy, so you can just, so this I ask you to do by exercise now. Y index of tzk is equal to, so this is an exercise. Okay, anyhow, so this is another idea of, but it's similar to proof of fundamental theorem of algebra, in a little more subtle, a little more difficult, but that's the same way. Okay, guys, so I think we stop now and then we come back because there's. Okay, so by a similar method, you can prove index theorem for generalized Dirac operators. So let me tell you what we mean. We have had this before, but let me just tell you. Remember, we had now let's kind of V over M, a Hermitian vector bundle. Plus a compatible connection, right? So we have this compatible connection. And this M is, of course, still a spin. And so then we have reconstructed actually this Dirac operator dV, which goes from C infinity of, M and S cross B to C infinity of M and S tensor, B, right? So this is more general in the sense that we have now these coefficients. And well, yeah, this is a kind of more general class of Dirac operators, right? And these are also, they have finite index and we want to compute the index. So the question now is index of dV plus is what? Well, in this case, actually, the topology of this V comes into the picture also. That plays a role, the topology of the bundle. So it's going to be integral over M. There is this part has to be there, a hat of Tm. And then Chern character of this comes into the game, Chern character of V. Okay, so now you can see that this is a inhomogeneous form. This is an inhomogeneous form. You multiply them and you pick the top part, you integrate, you get this index. So recall that Chern V, we had a, this is one of the, that's the first characteristic class that we discussed, right? This was like a trace of exponential of minus r over 2 pi I. Well, this r is this curvature of V, the curvature form of V. I mean, I use the notation for curvature form of Tm, but okay, you realize. So this is the Chern character, of course, the first characteristic class we discussed, and this is the form. So idea proof is similar. In this case, you just use the Weizenburg formula in the following form, because then Weizenburg is of the form the V squared is equal to, this dV squared is equal to nabla star nabla. Remember, we had the 1/4 of scalar curvature in the previous case. But now in this case, because we have this V, so this has contribution. So this curvature tensor of this comes into the game, R. Maybe there is some coefficient, I don't remember now, but then there is 1/4 scalar curvature. So this is just scalar curvature of the Riemannian manifold M. Has nothing to do with V. This is like before, so this is 0. Okay, scalar curvature of M. Okay, now the new ingredient in this case, there's this extra term R, and okay, so there are some, I guess there are some details, but essentially the proof is the same. I mean, proof goes through. Okay, so this is, I mean, now it's very important to be able to use the formula to prove cases. I mean, so now our goal for next week is going to be final week, because we have this Wednesday, I think, is holiday, next Wednesday. It's a long weekend, and the university closes on Wednesday. So, but we have Monday still. So I think this is going to be last lecture. Well, technically we have the week after, but I think it's enough to finish next Monday. So, I mean, then the plan is to use these two formulas to derive signature theorem, Gauss-Bonnet theorem, Riemann-Roch theorem, all those cases. But today I finished by writing one result, which is very standard. So this is the corollary of Atiyah-Singer for Dirac. So let M be a compact spin manifold with a non-zero A-hat genus. Then M does not admit a metric of positive scalar curvature. Then M does not admit a metric, I mean Riemannian metric of positive scalar curvature. So this is a kind of one of the kind of very standard applications. I believe this is due to Schneerowitz. This is all. I don't know if he used index theorem. Maybe he did use index theorem, or maybe he had another proof. I don't remember. I don't know. Really remember. So, but anyhow, so the proof is quite easy using index formula. If M admits such a metric, remember this metric is positive scalar recursion means K is positive everywhere, right? This means K is positive everywhere. And the K is not the constant, right? So it's a scalar function on your manifold. Then you can use this. Weizenburg formula, right? So this Weizenburg which was what? D squared equal to nabla star nabla plus K, implies that there exists no section such that the S equal to 0, right? So, in fact, if there is such a section, so we have D2 S equal to 0, this would imply that nabla star nabla plus K S equal to 0. So you can, you can take inner product of this, for example, with S again. So you get inner product nabla star nabla S plus Ks and S equal to 0. So this would give you nabla S. I mean, one hand, this is equal to 0, is equal to nabla S plus, nabla S plus K SS, right? So, well, this is positive if S is non-zero, and this is bigger than or equal to 0. So this would be a contradiction. So this would imply that S is equal to 0. Okay, so S is equal to 0. So this ds equal to 0 implies that S is equal to 0. So this, of course, remember what was D? D is equal to, 0, D plus, D minus 0. See, this already means that kernel of D plus and kernel of D minus are both 0. So this would imply that index of D is equal to 0. But we are saying that a hat genus, which is index of D, is not 0, and that's a contradiction of existence of metric of positive scalar curvature. And this contradicts with a hat of M not 0, because a hat of M exactly is index of D. So now this argument, okay, so the argument is finished. So the argument was easy. We started by, assuming the negative of that, and then we had this little device about computing the index in between. But then there was something which we tried. Now this is kind of nice. You see, this shows. What does it show? It shows the control that topology has over geometry, right? So, I mean, let me just, so this is sort of kind of relation between geometry and topology, which is very subtle. I mean, geometry is about existence of Riemannian metrics and curvature and this sort of, it's very rigid sort of information, right? And topology, they kind of sort of inform each other, and they somehow put restrictions on each other in sometimes very subtle way. But I mean, let me give you a much simpler case, or not case, really a feature of this. Simpler example. I mean, a simpler example is this. For example, on a Riemann surface of genus bigger than or equal to 1, there is no metric of positive scalar curvature. On a Riemann surface, I mean, compact, of course. I mean, this is not really Riemann surface. This is really Riemannian two-dimensional manifold. That's what I mean. There exists no metric with everywhere positive scalar curvature. Okay, topologically, all Riemann surfaces, I mean, Riemann two-dimensional oriented surfaces, they are of this form, right? We have complete classifications, topological classifications, and even smooth classifications, but not complex analytic. Complex analytic algebraic this is different. Okay, so that's, and you go on, right? So from here to, there is no, this is genus on a Riemann surface, of genus, I'm sorry, of genus bigger than or equal to 1. Of course, on the sphere, there is a metric of positive scalar curvature, rounded, no. Okay, so here, there is no such metric. So, for example, this manifold of this type, there is no metric whose curvature is always positive. So if you have a Riemannian metric on this or here, there must be a point where the curvature becomes negative, no matter what metric you put. How do you prove such a statement? So this is a statement about geometry, right? About the existence of a metric of a certain type on this manifold. I mean, in general, I mean, it could be hard, but again, the idea is to use this index theorem. So proof, you use Gauss-Bonnet. I mean, what does Gauss-Bonnet say? It says that Euler characteristic of sigma is equal to 1 over 2 pi integral over sigma. Basically, this is Gaussian curvature now. And this is the area for this is Gaussian curvature. Okay, but what is Euler characteristic of this? I mean, this is 2 minus 2g. This is pure topology, right? So if g is bigger than or equal to 1, this is less than or equal to 0. Always. Well, Euler characteristic in this case is 0. We know this case is minus 2. Yeah, I mean, then this is minus 4 and so on. These are all negative Euler characteristics. Only 0 in this case. Of course, chi in this case is 2. Okay, so now we have this contradiction. If such a k exists, it would imply that Euler characteristic is positive. But we know that it is not. So it's exactly the same spirit. Of course, this is much more complicated because there is this subtle, more subtle invariant, much more subtle than Euler characteristic. This is the A hat genus. We will see some computations related to this soon. So, I mean, okay, so, but it's the same spirit. Right? Now, of course, we can turn around and ask another question. Assume that this necessary condition is satisfied, namely Euler characteristic, for example, is negative. So the question is, what kind of question we can ask? The question would be, is there for example, one possible question is there a metric whose scalar curvature is always negative, for example, if Euler characteristic is negative? Or, yeah, for example, in this case, if a hat genus is 0, does it admit a metric which is always as positive scalar curvature? These are kind of interesting questions and usually quite hard to answer. But this is kind of first thing one can derive from index theorem. Okay, guys, so I think we are good now. So I think I